All right, so now I'm going to talk about how to construct numerical integration formulas based on interpolation. And part of the reason for doing this is that many integrals of seemingly simple functions cannot be analytically computed. So for example, the integral of e to the minus x squared dx. Okay, so that's something which you can't analytically compute. And the reason why that's significant is because this is the error function which shows up in probability and statistics. It's the normal distribution basically, right? Up to a sort of normalization. So this integral sort of is important. In probability and statistics. Okay, so it's the error function, ERF of x, which is defined to be 2 over the square root of pi of the integral from 0 to x of e to the minus t squared dt. Okay, so the point is that you can approximate that definite integral numerically, right? So the definite integral can be computed, can be approximated numerically. And these formulas for computing the approximation of these definite integrals are called quadrature rules. Or quadrature formulas, right? Okay, so so that's again sort of the basic motivation is that not again every function can be analytically integrated, but oftentimes even though you can't analytically integrate it, you might want to compute the definite integral, or at least approximate it to sort of an arbitrarily high order of precision. And one way to do this is to look at numerical methods known as quadrature rules. So let me sort of briefly talk about one very standard and straightforward way of constructing such a quadrature rule. Okay, and it's sort of similar to the the introductory lecture I mentioned, where you take the function and you approximate it by some sort of polynomial interpolant, and then you exactly integrate that polynomial. Okay, so that is actually exactly how you go about doing this. So this leads to what are called Newton-Cotes methods, Newton-Cotes formulas. Okay, so you have an integral from a to b of f of x dx. All right, and you replace f of x by a polynomial interpolant. Okay, let's call that p of x. Okay, so the integral of ab of f of x is approximately the integral from a to b of p of x dx. And of course, the reason why that's important is because polynomials can be analytically, the integrals of polynomials can be analytically computed, right? So, so you write p of x in this Lagrange form. So you write p of x, which is the interpolating polynomial, in Lagrange form, which I talked about. Okay, so you get an integral from a to b of f of x. This is approximately dx, and this is approximately equal to the integral from a to b of the sum, right, from I equals to 0 to n of f at xi, where the xi's are the interpolation points, which you had talked about before. And then you have to multiply this by the Lagrange polynomials. J goes from 0 to n, but j is not equal to I of x minus xj over xi minus xj. All right, so that's what I'm calling p. And I integrate that with respect to x. Okay. All right, that's quite a handful, right? There's a integral, there's a summation, there's a product. All right, okay, but you know, you can reorder them, and that's what we're going to do. All right, and in particular, I'm going to take the sum out of the integral. So this is equal to the sum from I equals to 0 to n of, okay, and f of x doesn't get affected by the integral, so I take that f of x out. All right, f of xi. Sorry, f of x, it's like it gets affected by the integral, but f evaluated xi is just a scalar, so that doesn't get affected by the integral. So f of xi can be taken out, and then there's an integral from a to b of this product from j equals to 0 to n of j not equal to I of x minus xj over xi minus xj. Right, and as we had discussed before, this is the Lagrange polynomial, right? Oftentimes denoted as Ln, I of x. Okay, and that is a polynomial of degree n. Okay, so it's polynomial degree n in x. Okay, so that's obviously something which you could integrate analytically. Okay. Then, so again, it's like that's showing you that if you want to compute the integral of some function, it's like where you happen to know it's like the function values at a bunch of interpolation points, right? Then you can construct this thing, and then this coefficient, right, can be computed. It's just a number at the end of the day, right? This whole thing is just a number, which depends on a and b, and it depends on the quadrature points, or the interpolation points. It's like x0 to xn, okay? But if you fix a and b and you fix x0 to xn, it's like then that number is fixed, and then you can use it to evaluate any integral from the form of from the interval a to b. It's like of this with those interpolation points. Okay, I should say that in practice, of course, that's perhaps not the most convenient setup, right? So you don't really want to have a formula which depends, it's like on what the limits of integration are. And so what you basically do, it's like which we'll show in a little bit, right, is that you do a change of variables, it's like on the integral, so that this interval from a to b gets sort of normalized to an interval from, say, 0 to h, for example, right, or 0 to 1. So you can sort of do a linear change of variables, if you will. It's like to change the limits of integration. It's like, and then that ends up giving you something which, you know, it's like then becomes a constant. So so that's helpful to do, and so we'll see that how to do that in a little bit. Okay, so in any case, so that's not quite the Newton-Cotes method, because the Newton-Cotes method is like assume something about the xi's. So in the Newton-Cotes method, the xi's are all sort of equally spaced from each other. Okay, so that's what gives them that Newton-Cotes form. All right, so I should say that. So if x0, x1 to xn are equally spaced, and this formula here is known as the Newton-Cotes formula. Okay, so let's look at simple examples of this. And perhaps the simplest example you could have is if you just have piecewise linears, right? So if you have a linear interpolant obviously correspond to situations where the data only has 2 points, okay? Or where you only evaluate the data at 2 points, okay? So for n equals to 1, the Newton-Cotes formula is the trapezoidal rule. Okay, so you can check that that is indeed the case. All right, so let's see how we do that. P1 of x is going to be f at a, x minus b over a minus b, right? That's the, I'm writing down essentially the first order, it's like Lagrange interpolating polynomial, right? Plus f of b, x minus a over b minus a, right? So that's literally the Lagrange polynomials here. These are the function values at the 2 endpoints. Okay, so this is the first order linear interpolating polynomial, right? So if you have a and b, this is f of x, right? Then p1 of x is exactly this expression here. Okay. All right. So you can actually sort of see from the picture, right, that if p1 is that interpolating polynomial, then the integral from a to b of p1 of x dx, right, is just going to be 1/2 times b minus a times f evaluated at a plus f evaluated at b, right? That's just the area under the curve. Okay, for P1. Okay, so that's obviously just the trapezoidal rule, right? Which is the trapezoidal rule. Okay, which is sort of what we had said before. Okay. So, so what you can do is you can try to compute the error, right? So what is the error? Okay. So the integral from a to b of f of x dx minus the integral from a to b of px dx, right, is equal to 1 over n plus 1 factorial, the integral from a to b of f, the nth plus first derivative of f, right, at cos cx, some unknown point, times this product L equals to 0 to n of x minus xl dx, right? So this is just the remainder term. So this is the remainder term, it's like which tells you the difference between f of x and p of x, right? Or pn of x to be more precise. And well, with this 1 over n plus 1 factorial term. Okay, so if f of x minus p of x is 1 over n plus 1 factorial times the nth plus first derivative f at some point times this product of linear factors, then obviously the integral of this is of this error is the integral of this remainder term, right? So that's basically what you might expect, and this is sort of just a very clear indication of how the approximation properties, it's like which you first establish in the context of interpolation, then leads you to the error analysis of the quadrature rule, right? Because this integral here, as we sort of talked about before, is exactly your computable approximation, right? It doesn't look like it, but it turns out to give you a computable approximation, and this is obviously the integral which you want to compute. And then you can write this error as the integral of the remainder term in the polynomial interpolant, right? Okay. So let's look at the special case again of the trapezoidal rule and see what happens. So for the trapezoidal rule, right, n is equal to 1. So this gives you that the integral from a to b of f of x dx minus the integral from a to b of, let's write it p1 of x dx is equal to 1/2 the integral from a to b of f double prime at some unknown point, x minus a, x minus b, right, dx. Okay, so this is equal to 1/2 f double prime at some new point, integral from a to b, x minus a, x minus b, dx. Okay, so going from here to here, right, is the mean value theorem. So this is the mean value theorem for integrals, which I can do since x minus a times x minus b has the same sign. Throughout the interval which I have from a to b. Okay. All right, so going from here to here allows me to take this f double prime term out, and then this term I can, in principle, evaluate, right? Or actually, I can evaluate, not just in principle, right? This is just a quadratic polynomial, which I can integrate. So this gives me minus 12b minus a cubed f double prime at some point. Okay, so again, it's like that tells you what the error is, right? So it's cubic, basically. In the leading order error term is cubic. It's like in the length of the integration domain. It's like, and then it involves some second derivative. So again, in order for the trapezoidal rule to make sense and to give you a reasonable approximation of the integral, right, especially as you let the interval go to 0, right, you have to have control over the second derivative of the function you're applying it to. Okay. So that's basically what I wanted to say about quadrature based on interpolation, at least at the start. We're going to look at sort of higher order methods based on this, but this sort of gives you, the big picture idea, and then we'll follow up in a little bit. So I'll stop here for now.